This is an AQA GCSE Chemistry Higher Tier Paper 2, talk through from June 22. This question is about copper wire and copper compounds. Copper is used to make electrical wires. Figure 1 shows how copper electrical wire is insulated using an addition polymer called polybutene. The addition polymer polybutene has the displayed structural formula. Polybutene is produced from the monomer butene. Complete figure 2 to show the displayed structural formula of butene. Because it's an alkene, it has a double bond, and then we just need to complete with single bonds. Copper can be obtained by recycling scrap copper wire. Suggests why polybutene insulation must be removed from scrap copper wire before the copper is recycled. Well, the copper wouldn't be copper then, would it? It would have that plastic on it, so not so useful. Describe how scrap copper wire can be recycled to make new copper water pipes. So we have copper wire, we need to turn it into copper piping, so we need to melt the copper and reshape or remold into copper water pipes. Suggests 2 reasons why recycling scrap copper is more sustainable than extracting copper from copper ores. Well, recycling typically requires less energy and it helps conserve our copper ore. It also means there's less waste. Copper sulfate is a compound of copper. Copper sulfate solution contains copper 2 ions and sulfate ions. I can feel a chemical test question coming on. A solution can be added to copper sulfate solution to show the presence, name the solution, give the result. Okay, the solution is sodium hydroxide and it's a precipitation reaction, which if you have copper 2 ions, you'll get a blue precipitate. Describe 1 test to show the presence of sulfate ions, give the result of the test. So this time we're adding hydrochloric acid and barium chloride, and you will see a white precipitate if you have sulfate ions present, because that white precipitate is barium sulfate. If you're not comfortable with the formula, feel free to write it out in words. Question 2, a student investigated the change in mass when hydrated cobalt chloride was heated. The word equation is hydrated cobalt chloride produces anhydrous cobalt chloride and water. This is the method used. Add 2 grams of hydrated cobalt chloride to an empty test tube. Measure the mass of the test tube and contents. Heat the test tube and contents gently for 30 seconds. Allow the test tube and contents to cool. Measure the mass of the test tube and contents. Repeat steps 3 to 5 until you've reached constant mass. Table 1 shows the results. Look, we've reached constant mass here. Determine the mass of the empty test tube. So to find the mass of the test tube, we want to do the mass of the test tube and contents minus the mass of the hydrated cobalt chloride to get 24.5 as our answer. Explain why the mass of test tube and contents decreased. Well, when you heat it, you're going to drive off that water. So you're going to go from having a hydrated cobalt chloride to having a dry cobalt chloride. So when heated, water vapor was produced which escaped the test tube. Suggests why the test tube and contents were heated until the mass did not change. In that way, you know that the reaction was complete. Energy is taken in from the surroundings when hydrated cobalt chloride is heated. That actually means it's an endothermic reaction. When 238 grams of hydrated cobalt chloride is heated until the mass does not change, 88.1 kJ of energy was taken in. A student heated 2 grams of hydrated cobalt chloride until the mass did not change. Calculate the energy taken in during this reaction. Give your answer to 3 significant figures. Effectively, we need to work out what proportion of 88.1 kJ of energy is taken in. So we do the 2 grams we have in the question divided by 238. And then we multiply it by 88.1 kJ to get 0.7403 kJ. And we need that to 3 significant figures. Always check the wording of the question. What type of reaction takes place? I've already mentioned that because heat energy is taken in. It's endothermic. This question is about life cycle assessments. Milk bottles can be made from glass or from a plastic polymer. Table 2 shows information about the milk bottles of equal volume. Right, let's look at the raw materials. So, crude oil is non-renewable, that's an issue. But we do know that quarrying to get this limestone and sand is going to be a problem for the environment. Energy needed to process raw materials is much higher in glass compared with the polymer. Energy needed to manufacture the bottle, again, it's much higher for the glass. The mass of the bottle is heavier. Mean number of times, okay, look how many times that glass bottle can be used versus only once for the polymer. This is why it's so bad for the environment. One disposal method, end of useful life. The glass is amazing, it can be recycled to make different glass products, but again, the polymer can also be recycled. Evaluate the use of glass for milk bottles compared with the use of a polymer. Use features of life cycle assessments. So life cycle assessments is all about looking at the environmental impact of the manufacture, the harvesting of the raw materials, and then disposal of the end product at the end of its life. So we're just going to use the data from the sheet. So I'm going to start by talking about raw materials. Let's try and write in full sentences, something I struggle with. In terms of raw materials, crude oil is finite. The limestone for glass bottles has to be quarried. Glass uses, this is all data in the table to process the raw materials. Moving on to the manufacturing process. In terms of manufacturing, glass uses more energy. Remember, the manufacturing also involves the transport. Transporting glass uses more energy because glass weighs more. Major advantages of glass is they can be used far more times. What about the disposal? Both glass and polymers can be recycled. Which reduces landfill. Don't stress about these questions. Honestly, just use each row of the table and make a statement. Milk is also sold in cardboard cartons. A carton is made using 40 centimetres cube of cardboard. The density of cardboard is this. Calculate the mass of the carton using this equation. I suddenly thought, am I doing a physics paper here? Don't worry about rearranging the equation if you don't want to. Look, sub in that density value. We're after mass. The volume is 40. The answer is 16 grams. This question is about the fractions obtained from crude oil. Crude oil is separated into fractions by fractional distillation. The fractions obtained from crude oil include lubricating oil, naphtha, petroleum gases. Table 3 shows the boiling point range of these fractions. Explain how these fractions are obtained from crude oil by fractional distillation. Okay, please just learn this answer. So we heat the crude oil until it evaporates. Pass the vapour into the fractionating column. The gas rises, cools, and condenses at different positions within the column. This is because the column has a temperature gradient and the fractions have different boiling points. Fractions from crude oil can be processed to produce feedstock for the petrochemical industry. Which two are useful materials produced from this feedstock? Again, something to just learn off by heart. It's detergents and solvents. Another fraction obtained from crude oil is petrol. Petrol contains a hydrocarbon with the formula CnH20. Complete the equation for the complete combustion of CnH20. Balance the equation. The key thing here is you have a plentiful supply of oxygen, meaning that you're going to make carbon dioxide and water as your byproduct. Do remember that oxygen is diatomic. The easiest thing now is to get your carbons balanced. You need a 9 here. Then get your hydrogens balanced. We have 20 here, so we need 10 here to make 20. And then sort out how many oxygens you have. You've got 18 oxygens there, 10 over there. So in total you have 28. Which means you need 14 here. Petrol obtained from crude oil contains sulfur impurities. Explain why sulfur impurities are removed before petrol is burned in car engines. Because when burnt, sulfur impurities produce the gas SO2, sulfur dioxide, which dissolves in rainwater, forming that dreaded acid rain. Table 4 shows some information about 2 more fractions obtained from crude oil. A student predicted that heavy fuel oil is more viscous than kerosene. I'd expect that. Yeah, cool. The student's prediction was correct. Justify the student's prediction. It's because it's got a longer chain of carbon atoms, which means it's going to be thicker, which means, again, more viscous. So as fuel oil has more carbon atoms, and as the number of carbon atoms increases, the viscosity increases. Remember, viscosity is how thick a substance is. Honey is very viscous, water is not viscous. The heavy fuel oil fraction can be processed to produce smaller hydrocarbon molecules. Name the process which produces smaller hydrocarbon molecules. Give the conditions used. This is cracking. You need a catalyst. Lots of options. I'm going to go with alumina, and you need a high temperature of around 600 degrees Celsius. Hydrocarbon molecules containing 7 and 8 carbon atoms can be produced when heavy fuel oil is processed. Which pair of hydrocarbon molecules would both turn bromine water colourless? This means we need an unsaturated hydrocarbon, something like an alkene, which obeys the formula CnH2n. That obeys it. This also obeys it because it's obeying CnH2n, so don't go any further. That's your final answer. This question is about water. Sewage is wastewater. Sewage contains organic matter. Describe how sewage is treated to remove organic matter. We need filtering, first of all, to remove solids. Sedimentation then occurs to allow soluble solids to sink. And then it gets a bit gross. We have anaerobic digestion of the sludge produced. How very technical. And anaerobic means no oxygen is present. And then we have aerobic biological treatment of the effluent. Seawater and groundwater are treated to make them potable. That means suitable for drinking. Table 5 shows information about the composition and treatment of seawater and of groundwater. Concentration of sodium ions and chloride ions before process 1. So yeah, seawater is salty, so expect it to contain a lot of sodium and chloride ions. Groundwater is not salty, and as you'd expect, far less. Process 1, reverse osmosis. That requires an awful lot of energy. Process 1 for groundwater is filtration, which means removing solids. Concentration of sodium ions and chloride ions after process 1 to be determined. It's the same for groundwater. Process 2, add ozone for groundwater exposing to ultraviolet light. Seawater is desalinated during process 1. Which pair of concentrations could represent X in table 5? So yeah, we want much less by way of concentrations. So this is the answer. Explain why the concentrations of sodium ions and of chloride ions in the groundwater in table 5 are unchanged by process 1. So if we go back, look, filtration was that first process. Filtration is not going to trap the ions. Remember, this is all to do with stopping solids. Those ions are far too small and will pass straight through the filter. Explain why the groundwater in table 5 requires process 2 before the water is safe to drink. Process 2 is exposure to ultraviolet light. That will kill any pathogens present and make sure that water is sterilised. After treatment, the groundwater in table 5 is sold by a company as pure water. The groundwater in table 5 is not chemically pure because the water contains sodium ions and chloride ions. Suggests what the company means by pure. Yes, I mean, it's not a very technical state, is it? You can actually get away with saying that it's water with nothing added. I'm going to just say water contains no pathogens. Or you could say that it's in its natural state. Chlorine is also used to treat some groundwater. Describe the test for chlorine gas. Give the result of the test. Hold gas over damp blue litmus paper. What you see with chlorine is that litmus paper turns white or is bleached. This question is about the chemistry of the Earth's atmosphere. Figure 3 shows how the percentage of gases in the Earth's atmosphere may have changed since the atmosphere was formed. Double check all these gases. So carbon dioxide levels have drastically decreased. Nitrogen levels have increased to around 80%, which we know to be true. It's around 78% now. And then oxygen levels started at near enough zero, and then they have increased to around 20%. Explain the change in the percentage of gas in the region labelled A. So we're zooming in here. So why have nitrogen levels increased? Remember, that's because of intense volcanic activity. Explain the change in the percentage of gas in region B. So this is carbon dioxide. It has dramatically decreased. They don't want an answer to do with plants photosynthesizing, actually. They want that CO2 locked up in the oceans. Compare the changes in the percentage of gases in the region labelled C. So we can see over here in C that oxygen levels have increased and carbon dioxide levels have decreased, and that, look, those gradients are pretty similar, so that percentage increase and decrease is occurring at a similar rate for both. So percentage of CO2 has decreased, percentage of oxygen has increased. The increase and decrease of these gases has occurred at a similar rate. What process caused the changes in the percentages of gases in the region labelled C? That will be photosynthesis, because plants use up carbon dioxide in order to make glucose. So that's what's going on with this dotted line, and then they release oxygen as a byproduct, which is why it's increasing. Natural gas is a fossil fuel. Describe how deposits of natural gas were formed. Plankton died millions of years ago. And became buried under lots of layers, high temperatures and pressures, produced natural gas. Hence why it's such a finite resource. Ammonia is produced in the Haber process. The raw materials for the Haber process are nitrogen and hydrogen. The equation for the reaction is: give the sources of the nitrogen and hydrogen used in the Haber process. Nitrogen, remember, it comes from the air. 78% of our air is made up of nitrogen. Hydrogen comes from natural gas. How does the equation for the reaction show that the atom economy of the forward reaction is 100%? Based on the fact that you only get one product. So you've got an entire conversion to that useful ammonia with no byproducts. Figure 4 represents the Haber process. So we've got nitrogen and hydrogen entering the reactor. Then ammonia is being produced, and any unreacted nitrogen and hydrogen is recycled. Explain how the ammonia produced is separated from the unreacted nitrogen and hydrogen. So we're going to cool it down so that only the ammonia liquefies. Or condenses. I prefer the word condenses. The Haber process uses a temperature of 450 degrees and a pressure of 200 atmosphere. Table 6 shows the percentage yield of ammonia produced at 450 degrees using different pressures. So as we can see here, increasing the pressure increases the yield. Complete figure 5. The first 2 points have been plotted. You should use a suitable scale for the x-axis. Plot the remaining data, draw a line of best fit. Pressure in atmospheres, yeah, that's fine. Then we're going to have a look. We go from 60 to 420, 100, 200, 300, 400, 500. What about this data? 180 and 25. 240 and 31, 336, 360 and 40, 420 and 43. Here's our line of best fit. Do make sure you've done all of these things. Tick them off in the exam. Determine the percentage yield of ammonia at 450 degrees and 500 atmosphere. So we read up and then read across. So that is around 47, 46. The equation for the production of ammonia in the Haber process is this. The forward reaction is exothermic. Remember, that's therefore favoured by a low temperature. So high yield of ammonia is favoured by a low temperature, but you get very low rates of reaction. Remember, collision theory will be important here. The conditions used are the following: a pressure of 200 atmospheres, the presence of an ion catalyst. Explain why these conditions are chosen for the economical production of ammonia. You should include references to rate of reaction and position of equilibrium. This is a great opportunity to score 6 marks. So we're going to start by saying high yield of ammonia, and we need to talk about it from both a pressure and temperature point of view, are favoured by, number one, low temperature. Why is that? Because the forward reaction is exothermic. They've told us that in the question, and therefore the position of equilibrium, they've asked me to mention that, so that's why I'm talking about it here. I'm writing that as a condensed form, shifts to the right, which is what we want to make more ammonia. But low temperatures mean low rates of reaction because particles have less kinetic energy. So less frequent collisions occur. So that's the hardest bit done, really. Now we need to talk about pressure. So count the number of moles of gas. There's an invisible one there. There's 3 there. So there's 4 moles on the left, 2 on the right, which means to move the position of equilibrium to the right, we want to increase the pressure. So we'll write high yield of ammonia needs a high pressure, as there are fewer moles of gas on the right hand side. So position of equilibrium shifts to the right. The good thing about high pressure is that that also favours a high rate of reaction. But high pressures are dangerous and expensive. Running out of room. Last up, this presence of an ion catalyst. I have run out of room. We're going to say that it increases the rate of both the forward and reverse reaction and has no effect on yield. And the examiner had better be pleased with this answer because I think I've covered all bases. This question is about the reaction between sodium thiosulfate solution and hydrochloric acid. When hydrochloric acid is added to sodium thiosulfate, the mixture gradually becomes cloudy. Sulfur is produced in the reaction. Why does the mixture become cloudy? Because you've produced a solid or a precipitate. Use those state symbols to help you. A student investigated the effect of changing the concentration of sodium thiosulfate solution on the rate of reaction. A small percentage of the light from the light source reaches the light sensor as the mixture becomes cloudy. This is the method used. Measure 50 centimeters cubed of 0.1 mole sodium thiosulfate solution into the beaker. Add 10 centimeters cubed of HCl. Immediately start a timer. Record the percentage of light from the light source that reaches the light sensor every 20 seconds for 120 seconds. Repeat steps 1 to 4 but using a higher concentration of sodium thiosulfate. Figure 7 shows the results for the 0.1 molar sodium thiosulfate. As you'd expect, as the experiment goes on, the percentage of light from the light source reaching the light sensor decreases because of that solid sulfur that was made. The percentage of light reaching the light sensor decreases by 1% when 7.1 times 10 to the minus 5 moles of sulfur is produced. Determine the rate of reaction in moles per second for the production of sulfur at 30 seconds. You should draw a tangent. 5 marks. So here's 30 seconds. Then draw a tangent nice and accurately. And then to find the rate of reaction, all we have to do is find the gradient of that tangent, which is change in y over change in x. So carefully read off your y-axis. It's 40. The x-axis is, that's 15. That's 55. So it's 40. So that gives us the ratio. And then to find the rate of reaction, we do the ratio we've just calculated times the number of moles. So that's effectively 1 times 7.1 times 10 to the minus 5. Explain why the rate of reaction changes between 0 and 60 seconds. Answer in terms of concentration. So we're looking along here. Why does it decrease? Simply because the rate of reaction is slowing because some of those reactant particles are being used up. Figure 8 is a repeat of Figure 7. Figure 8 shows the results for 0.1 mole sodium thiosulfate solution. Sodium thiosulfate solution was in excess. The line of best fit on Figure 8 is horizontal between 80 and 120 seconds because the reaction stopped. Why did the reaction stop? Well, we know that the sodium thiosulfate is in excess. So if we look back at the original equation up here, if this is in excess, we know that HCl is limiting and that it must have all been used up for the reaction to stop. Sketch a line on Figure A to show the results you would predict for 0.2 molar sodium thiosulfate solution. So because we've got a higher concentration of sodium thiosulfate, you'll expect a steeper gradient, but be careful in terms of where it levels off. You haven't increased the concentration or volume of hydrochloric acid, and therefore you'll still expect that final result to be the same. The same student did the investigation again the next day. The student found that the same method produced different results for the percentage of light reaching the light sensor. How could the student improve the method so that the same percentage of light reached the light sensor? It must mean that there were different levels of light. Maybe it was a cloudy day. So you want the ambient light in that room to be the same. So which of these options indicates that? Stop light from other sources reaching the light sensor. Yeah. The student improved the method so that similar results were obtained on different days. What name is given to similar results obtained on different days under the same conditions by the same student? This is all about repeatability and reliability. So it's this one. It's your ability to keep getting the same results. They might not be right, but they are the same. Figure 9 shows the volume of sodium thiosulfate solution of concentration 0.1 mole, hydrochloric acid of concentration 0.5 mole, which completely react to produce different masses of sulfur. Make sure you're happy with the key. This one's sodium thiosulfate, this one's HCl. Which expression represents the relationship between the volume of sodium thiosulfate solution used and the mass of sulfur produced? So as we look at this line here, you can see that the volume of reactant used and the mass of sulfur produced is a directly proportional relationship, which is why this is the answer. Determine the simplest whole number ratio of the volumes of sodium thiosulfate solution to hydrochloric acid, which completely react with each other. So we need to pick a fixed mass. Doesn't matter which one you pick. I am going to go for this one here, just because I know it will be easier for me to read off. So here we have about 48 centimetres cubed of sodium thiosulfate. Keep reading along. We have about 185 centimetres cubed of HCl. So to get it into a ratio, divide both numbers by the smallest number. So 185 divided by 48. So we want it to the nearest whole number, so it's 1 to 4.